everyone, and welcome to today's coffee and conversation with Dr. Daniel Swain. I am Jim Pfeiffer. I am the Executive Director of the Regional Water Authority. If you're not familiar with us, the RWA is a joint powers authority with nearly 24 water providers serving 2.2 million people across the greater Sacramento region. Since 2001, we've been working to serve, represent, and align the interest of our members to improve water supply reliability, availability, quality, and affordability. You can learn more about our work at rwah2o.org or sacwaterbank.com. And now I'd like to introduce your host for today's conversation, Ryan Ojakian. Ryan is RWA's Government Affairs Program Manager, leading advocacy efforts for the RWA. With over a decade of experience in the California legislature, he has served as a senior consultant for the Assembly Parks and Wildlife Committee and as a legislative director for Assembly member Mark Levine and a legislative aide for Senator Joe Simitian. Ryan holds a master's degree in economics from San Diego State University and a bachelor's in physiology and neuroscience from UC San Diego. Ryan, I'm turning it over to you. Thank you.
Thanks, Jim. I'm really excited today that we have Dr. Daniel Swain. I think all of you are likely familiar with his accolades. They are up on the screen. I think I'm going to give a little bit of an intro that's a little bit aside from what you see on the screen, but please do take in what you have on the screen. I think the reason why we're so excited to have Dr. Swain here today is he's really viewed as the lead, if not the trailblazer, on what is known as a climate communicator. That's really, just so critical in this time. I've seen it described as really that being one foot planted firmly in science and the other in sort of communication and being able to bring that science to the masses, so to speak. So I think a little bit more on Dr. Swain. For those of you that don't know, he was the person who coined the ridiculously resilient ridge. He has a really well-visited tweet saying, it's okay to shout fire in a crowded theater if there actually is fire in the crowded theater. And I think there's so much more to go on with that, but I do want to welcome Dr. Swain at this moment.
Well, thanks for having me today.
It's our great pleasure. So for those of you who are first-time coffee chats, this is it's intended to be a casual conversation. So I think hopefully you'll get to learn a little bit about Dr. Swain as well as get a frank and honest conversation in a more casual setting. Not that I think Dr. Swain would ever not give a frank and honest conversation or answer to any question, but again, we're really lucky to have him here. So what I wanted to start with, Dr. Swain, is a little bit about how you came to be so interested in weather. Now, one of the other things that I saw is that you're self-described as a weather geek, and I think that this comes from an interest very early in life. I saw some events when you were as young as 4, as young as 6. If you could tell us a little bit about how you came to be interested in weather in general.
Yeah, thanks for that introduction. There are a lot of meteorologists out there in the world who will tell you that they have some specific extreme weather event from their childhood that was a formative event, and then I guess equally as many folks who don't have that origin story. I'm somewhere in between. I always I think was interested in the natural world and in the atmosphere and the weather in general. There were a couple of particularly momentous, I guess, Northern California storm events in the 90s that I think were probably formative events for me. I grew up in the North Bay. And so, I do have that recollection of constantly looking up at the sky. And so, that's originally what I pursued professionally, was a degree in atmospheric science to become a weather forecaster. I thought I would end up working for the National Weather Service or something. And while that didn't end up happening, partly because at some point in that process, I became really interested in how uh, the weather itself was changing over time. And this seemed to be a bit of a gap, both in scientific knowledge and also in the public conception of what climate change was. So that was actually my point of entry into climate science and climate change, which was that original interest, that fascination with the weather, translating into a sort of an intellectual and then sort of societally motivated interest in how that weather is changing over time and why we don't have more understanding and more conversations surrounding it. So I went on to get my PhD in Earth System Science, still in the Bay Area for that. So I got my undergraduate degree at UC Davis, of course. So have spent a bunch of time in the Central Valley, then PhD at Stanford. So still in the Bay Area. Went down to UCLA to do postdoctoral training, and today, as you say, I live with a foot in, I almost said both worlds, but actually multiple worlds, personally and professionally, where I have my primary appointment is with University of California Agriculture and Natural Resources as essentially a climate scientist who has a public-facing mandate, so whose job description is, in fact, to speak with any number of different audiences, with journalists, with the general public, with policymakers, but also continuing with UCLA's Institute of the Environment and Sustainability, and also the NSF National Center for Atmospheric Research. So all of this essentially lets me continue to be a bit of a weather geek. In fact, just yesterday I was recording for the third time an episode of the Weather Channel Weather Geeks podcast. And it's funny really going full circle. I've gone from watching the Weather Channel as a bit of a weird kid growing up to now being on the Weather Channel about once a month as an invited guest to talk about weather and climate, which is pretty fascinating. Some of those folks I saw on TV growing up are now the ones interviewing me in these sessions. So it's an interesting journey, and it's a little bit of an unusual one from a climate scientist perspective, because a lot of climate scientists come from other fields of physics or chemistry or biology, and I come into it from meteorology, literally from weather science. And so that is sort of my scientific approach, is thinking about climate change as changes in episodic weather events. So sort of weather in aggregate is the climate. So if the climate is changing, therefore weather in aggregate is changing. And also as a point of entry for having conversations like the one we're having today, where I think a lot of people's interaction with the atmosphere is most obvious day to day. You choose what clothes to wear, you decide whether you need an umbrella. If you work on a farm, that's really going to dictate, what you're able to do day to day. So these episodic weather events really affect our day-to-day lives, and that is sort of my connection in talking about those as such, and then also in a broader context of how they're changing over time with the warming climate.
Thank you so much for that answer. There's a lot to build off of there. I am going to say, though, that for purposes of today, at least, I think always we're going to claim you as one from our region, given your UC Davis, your time at UC Davis. I do want to, I think you touched on this in this question, and I do want to ask this as background, but build on this a little bit more, because I want to underscore this point for the audience that you're sort of one of a kind in some respects, in sort of being, again, a trailblazer on climate communicator. One thing that I saw from, I think one of your, someone who helped create the position for you at UCLA, and I say create the position because this is a unique position, and it's really, I think, a little bit more about, should it be more mainstream, right? That we have people who are speaking from a science background in a way that is more accessible and available to the general public. Because I think we're living in a time where, and I will open it up. This is a little bit of a loose-ended question here, but we're living in a time where sometimes we're not tethered to science and tethered to facts in sort of decisions and policies that people are making. And so I think, I guess, again, I'll try and bring this home a little bit more, but the question is really how, and this may be challenging, how can we have more of you? How can your position not become something that's unique and really, I'm sure you had to advocate and carve out, but something that is more mainstream and accessible for those who aren't either interested in putting in the time to create their own path or just have the really ability to create their own path. So I hope there was a question in that. I promise you we'll get to more concise questions after this, but I did want to open it up and allow you to sort of give your thoughts on that. How can we have more of you?
Yeah, well, first of all, it's a bit humbling, and I would suggest that perhaps it's not so much that I am unique as much as that I've been through some combination of maybe persistence, maybe you could call it obstinance, good luck, and strong advocates on my behalf. You know, I've been able to do what I do today in this, and it hasn't been a particularly simple or straightforward path. That's certainly true. I would call myself a climate scientist communicator with a hyphen in between scientist and communicator, because I don't actually really have formal training in communications. I'm trained as a meteorologist and as a climate scientist, but I end up spending at least half of my time in what is effectively a communications role. But I also, as you mentioned, continue to be involved in the production of new scientific knowledge, crank out those peer-reviewed scientific papers, write that analysis code, look at those Earth observations directly. So I really am sort of embedded with a foot in both of those worlds. And historically, they were fairly different worlds. You know, there has actually been relatively few opportunities for scientists to become really deeply enmeshed both in the science itself, truly actively involved in the science, and then also in the public facing conversations surrounding that science in real time. And there are very practical reasons why that's been the case. For a long time, quite frankly, and this is still true in some circles, it was viewed as highly inappropriate for scientists to engage the public, to speak colloquially in any accessible way with anyone outside the scientific world. There was this notion that scientists, that it is somehow desirable to speak an overly technical language that is essentially inaccessible to anyone outside of your subspecialty, because anything short of that would be insufficiently rigorous. You could say insufficiently insular, but that's, I guess, a matter of opinion. But I think the idea is that scientists do science, communicators communicate, and never the twixt shall meet. And I think that has been a big mistake. And the reason why there aren't more people in roles like mine was sort of like a 50-50 split between creating the scientific knowledge and truly spending a lot of time disseminating it is, frankly, a practical constraint of time and money. And as boring as it is to talk about constraints of time and money, I think this is a pretty important conversation to have, as you say, in this moment in particular, where context providing institutions have become weaker and fewer, and in a moment where we really need more of them, because you could argue one of the meta crisis of society today, well beyond climate and water and on all of this, is that it's really difficult to have focused or sufficiently nuanced conversations about any number of complex topics that have arisen recently in a way that is both honest and constructive, and then gets us to a point where we can actually think about how to solve these problems rather than focusing on blaming individual people or entities for perceived failures, or focusing on super narrow technical solutions to what are in a broader sense, much broader problems. And I'm being deliberately vague here because this isn't just a climate change problem or a weather or a disaster problem or a water problem. It's sort of an everything problem. It's a pandemic problem, a geopolitics problem. information and misinformation and disinformation problem. And so, but the problem is that the people who are responsible for generating some of that nuanced knowledge, whether it's in climate science or virology or anything else, don't really have institutional support to do both. You're a scientist or you're a communicator. And so I'm lucky that I've had people who've supported me at different stages, all the way from sort of a PhD level. I was at Stanford. My advisor, Noah Diffenbaugh, at the time was very supportive and remains today, even though I haven't been a PhD student in almost a decade, very supportive of my continued efforts. And then, as you mentioned, at UCLA, the Institute of the Environment and Sustainability, the person who was running that institute at the time was Peter Kariva, and he was really supportive of carving essentially at some, I think, some considerable internal political cost to himself, carving out a role where science and public engagement were essentially on equal footing. We did it. It was a little bit of a shoehorned in to an existing role there. We made it work. But now, with my new role, primarily with University of California Agriculture and Natural Resources, I have another specific person to thank for that, Glenda Humiston, whose vision sort of made this possible again. And actually today, my new role as of November of last year, so pretty recently, is a direct match for what I actually do, rather than trying to shoehorn what I'm actually doing into a slightly different role. My job is now officially to be a scientist and a communicator. And that is rare because institutions have historically found it difficult to support people in those capacities. So I am both lucky, obstinate, somewhat fortunate that I've been in the right place at the right time, at least as much as anything else. But how do we do more of this? Well, I think institutions really have to decide that they're going to value these sorts of things explicitly. And it is, as boring as it is, I say, to talk about money and funding and institutional support. That kind of is the solution. Is if you want people to do this work, you have to support them, and but which in many cases means give them an income to actually do this work, rather than saying, oh, well, your job is actually to do science. So if you want to, nights and weekends, you can talk to other people about your science. But ultimately, if you want people in these spaces who really are able to get into the details because they're involved in understanding those details firsthand and producing that new knowledge, you have to create roles in which people can do both. Scientists or practitioners or domain experts, whether they're engineers or medical doctors or whatever, whatever your realm of expertise is, you have to have carve-outs within institutions, within roles where people actually have the time to do this on a sustained basis. Because, for example, I do about 200 to 300 news media interviews a year at this point. So on average, almost one a day. Yeah. And I don't think that I was originally as efficient or as good at speaking with the public or with the media as I am now. And I don't necessarily think it's because I have some special ability there. It's because, what they say about 10,000 hours of practice. Yeah. Once you do something hundreds or thousands of times, hopefully you get better at it, but you need the time and the support to engage at that level to get to that point.
Appreciate that answer again. Thank you for sharing. I do want to get into one thing that you touched on, and we're going to segue here a little bit in that answer about a multifaceted challenge. And so we'll get a little bit more, I think, into the science here. But the first question that I have in this area is, I've heard and seen that it takes decades for climatic changes to express themselves from emissions, right? So said in English, some of the changes that we're experiencing today are from when you were, as we were talking about earlier, very young, or even when I was quite young. Could you explain that process a little bit more? And then if you'd like, because I'm in the interest of time, talk about how those changes are sort of, again, exacerbating or putting fuel on the fire of the threats of flood, fire, drought here in California.
Yeah, I mean, I think there's two ways to think about this. One, in a very proximal sense, is that well, let's back up a little bit. That we know that climate change is happening, that global warming is real, and that the main reason that it's occurring, in fact, really, for all intents and purposes, the exclusive reason it's occurring at this point in time is the accumulation of heat-trapping greenhouse gases in the atmosphere as a result of human activities since about the mid-1800s. And the interesting part is that that does mean that emissions as far back as, during the Industrial Revolution over 150 years ago are still exerting an influence on the climate and therefore the episodic weather events that we're seeing around us today. But that most of that influence, though, most of that accumulation of greenhouse gases has actually occurred a lot more recently than that. So we can trace some of these initial changes all the way back that far. But the vast majority of these emissions have occurred just in the past few decades, because, of course, the annual amount that we're emitting and that's accumulating in the atmosphere has increased year on year pretty much continuously. In fact, even the last couple of years since the Paris Accord, where there was a goal to quickly level off and radically decline these emissions thereafter, that has not happened. We have continued to see further increases in net global emissions over the past several years. So in a certain sense, most of the warming that we've seen, most of the changes in extreme weather events that we've observed so far, is the accumulated effect of all of this warming that's occurred, this accumulated greenhouse gas concentration increase that's occurred over decades and even over a century or more. But it's also true that, the CO2 accumulation, the greenhouse gas accumulation that's occurring right now, so even, emissions that have occurred since January 1st of this year, 2025, they are already influencing the climate almost instantly and affecting what's going on around us. So it's not so much that there's a delay necessarily in the cause and effect between the emissions and the effects on climate. It's just that most of the effect on climate isn't, just as on a cumulative basis, isn't what's happened recently, but it's the overall effect of what's built up over decades. So it is both immediate and also lagged in the sense that most of the emissions that have occurred, prior to the last year or so, just as a matter of volume. But and this I think is important moving forward too, thinking about the future, because it's not so much that today's emissions we won't feel the effects of, for 20 or 30 years. We're feeling the effects of today's emissions right now. But maybe the more important way of thinking about this is, because we can't completely change our economy and our ways of doing business and getting around in industry and agriculture overnight, we're not going to zero out those carbon emissions overnight either. So it's not so much that we'll see the effects of today's emissions in 30, 40, 50 years. We will, because they're still going to be up there in the atmosphere, lingering and accumulating. But it's more that today's emissions, from the very high level of greenhouse gas emissions we continue to have today in 2025, we're not going to be able to shut those down so quickly that we won't have a lot of additional emissions moving forward. So it's sort of the socioeconomic and geopolitical inertia that's going to continue that warming for quite a while to come, more so than the geophysical inertia, if you will, of what we're seeing. And so it is there are different ways of thinking about this. But what we're seeing today, I mean, it is remarkable that the level of what we might call external forcing, which is a very jargony term, it just means essentially the magnitude of the human-caused global warming effect as a result of these accumulated emissions has roughly doubled in my lifetime. And as you say, I'm not that old, and so that's a pretty big influence. So was there global warming, prior to the 1980s? Yes, but the intensity of that human influence has essentially doubled over that period, and so that's not a small change at all in that kind of time scale.
Yeah, I mean, I would say that's a pretty dramatic change in that time scale. I do want to ask a little bit about how that change though is impacting our existing climate, particularly here in California, and particularly I think from a water perspective, but again, I think the water perspective has ramifications that are not just water supply, like drought, but also flood and even wildfire. I think we've Many in the audience may be familiar, right? But the atmospheric sponge effect, if I'm saying that correctly. And I think I will ask it maybe this way because we got this question in the chat. Is our water cycle broken, right, as a result of these climatic changes?
Well, this is another deep question, actually, so I'll address a few aspects of it. Obviously, in a warming world, temperatures rise, right? So you see more intense heat waves, more frequent heat waves. That's what you'd expect. And in most cases globally, we see a decrease in cold events, which actually ends up being fairly important for snowpack, for agriculture. So actually is quite relevant to California still, even though most Californians don't live in particularly cold or snowy places. There are snowy places in California, even if a tremendous amount of people don't live there, and they are of importance. So we see more intense, more frequent heat waves, to a greater extent increasing across inland areas versus the coast. So the coast is warming too, but not as quickly as the areas that were already hotter, go figure. And then there are the changes that we see, as you mentioned, to the hydrologic cycle through primarily due to what my colleagues and I have started to call the expanding atmospheric sponge effect. This was actually a term that I've been using for a few years. We officially published it in January in a review paper that came out. So I got past the editors, the colloquial language that I was arguing for. I think I'm glad it did, because I think it's a helpful analogy, which is really intended to represent the tangible effects of thermodynamics that have actually been understood since about the mid 1800s. So roughly since the Industrial Revolution, actually, this aspect of the thermodynamics of the atmosphere has been fairly well understood, which is to say that as temperatures rise, as air temperatures rise, the water vapor holding capacity of air increases exponentially. So even if you only increase temperature linearly by 1, 2, 3 degrees, whatever it is, the water vapor holding capacity of that air increases by about 3 or 4% per degree Fahrenheit of warming. So this is, as you might imagine, with like compound interest. If you have, interest in a bank, or worse, interest accruing on a loan or a credit card bill or something, it compounds. Each 3 or 4% is larger than the last 3 or 4% because it's 3 or 4% of what is itself a larger number. That's what's happening in the atmosphere. This is technically exponentially expanding. Atmospheric sponge has a greater and greater capacity to absorb water vapor and to yield water vapor. So the analogy being, like, think of an ordinary kitchen sponge that becomes progressively larger. You can soak up more and more water that you may or may not have spilled on your kitchen counter. But that expanding sponge has a greater water absorptive capacity, even if you haven't spilled that water on your counter. So even if it is dry, it still has the capacity to absorb more water. And the analogy there being that a warming atmosphere, when it is saturated, when conditions are favorable for precipitation, it can produce heavier precipitation. So if you wring out that larger and larger sponge and it's full of water, it's going to yield more and more water. But if it's not saturated, if it's dry, as is often the case in California, it's not raining more often than it is raining in California, and that's always been true in historical context as well. That expanding atmospheric sponge is going to retain that ability to evaporate more water, and therefore the atmosphere is thirstier. It's 3 or 4% thirstier per degree Fahrenheit of warming. And that drives greater evaporation, faster evaporation, if there is water available to evaporate, which there often is in California. So by the same token, this expanding atmospheric sponge effect increases the risk of extreme precipitation events on one hand, and potentially flood risk on that side of things. And then also the risk of extremely dry events, in other words, droughts, and also wildfires. And in recent years in California, we have seen more expansion on the dry side of the sponge. We've seen historically severe droughts more than once. We've seen historic wildfire conditions repeatedly, arguably not quite continuously, but every year or so. But I think to answer the questions that was originally asked is the water cycle broken? I think the challenge there is that the water cycle can't really be broken in a sense that the cycle is what it is, right? It can change, it can accelerate. And I think that's maybe the best way to think about what's going on, is that the water cycle is accelerating, and that the net balance of water is in some places shifting. The balance between evaporation and precipitation is in some cases changing. but it is in a sense always in balance because the water cycle is the net response to whatever the difference is in a particular place at a particular time between precipitation and evaporation. So it might be breaking our ecosystems and our human water systems in the sense that those are adapted to a particular balance that we saw historically, or a particular range of extremes that we're now increasingly outside of. So it's very possible for a shift or an intensification or an acceleration in the hydrologic cycle to break the ecosystems and the human systems that depend on its constancy over time. So that's very possible, and I think we are starting to see that. But the water cycle itself, I think it might be more accurate to say that it's accelerating largely as a result of this expanding atmospheric sponge, if you will.
Got it. So, I mean, I think, we say sometimes here, there's the same amount of water on the planet as when the dinosaurs roamed the earth. It's just in sort of different places, be it that in the atmosphere or in ice or, in groundwater. And so it's not broken, but it's changing in a way that we haven't seen in modern times, I guess, is maybe what I would say.
Yeah, I think that's fair to say. And I would say the same thing about folks sometimes who will use language like the climate is broken, and contrast that with folks who might say the climate is always changing and therefore the current changes are not a big deal. I think these
Yeah.
are almost two opposite ends of a spectrum that really just slightly misunderstands that, the climate is doing what the climate does. It's rapidly changing, and it's equilibrating to that rapid rate of change. And so in that sense, it's functioning as you would expect it to. But the problem is the change. It really is we would call it non-stationarity, meaning that the climate of today is different from the climate of 50 years ago, and the climate of 20 years from now will be different than the climate of today. It's the fact that it is changing rapidly over time. And of course, the climate does change over time. We know that there have been periods in the Earth's history when there have been palm trees in the Arctic, and when there's been ice sheets stretching down nearly to the tropics during cold periods in Earth's history. Obviously, we are not close to either end of that, fortunately, end of the climatological spectrum on Earth. But the problem is not that the climate is changing and that it's never changed before. Clearly it has. The problem is that the climate is changing very rapidly in the context of human civilization and stable ecosystems. And so it is a rate of change problem more than anything else. If the climate were rapidly cooling, that would also be a bad thing because it would be very hard to adapt to that rate of change as well. So it is really the change, the fact that things are shifting. As you say, there's roughly the same amount of water on Earth today that there was millions of years ago, but it's very differently distributed. And even with a similar distribution spatially, even if we're only talking about versus a few hundred or a few thousand years ago, because the continents tend not to move that quickly, the temporal distribution as well as the spatial distribution, this is what we mean by an acceleration of the height of the water cycle. Even if there is roughly the same amount of water falling in a particular place, averaged over 10, 20, 30 years. And this may well end up being true in California, actually, which is why I mentioned this. The overall annual average precipitation in California might not tremendously change even over fairly large amounts of warming, but the temporal distribution of that water could shift and is shifting quite dramatically. So you can imagine, just for really simple numbers, imagine there's a place that normally receives, 20 inches of rain in a year, and imagine that place over a decade sees 10 years with exactly 20 inches of rain. Okay, well, your average rainfall is still 20 inches. But now imagine you have instead 5 years where there's no rain at all, and then another 5 years where there's 40 inches of rain in each year. Your average rainfall is still 20 inches, but you have a very, very different hydroclimate, a much more amplified one. And that's, of course, a bit of an exaggerated example, but it just goes to show you how even the changing temporal distribution of that water can have profound influences, because you would plan very differently if you got a nice and even amount of water every year, rather than having some years where there's almost none and some years where there's double what you would typically expect.
So, very helpful answer. I want to sort of explore this a little bit more. I will take the time here to say, unfortunately, we only have an hour with Dr. Swain. We have 25 minutes or so left. His time is very valuable. We're not going to be able, I wish we had 2 hours. I wish we had 3 hours. But again, you know, as he mentioned, half of his time is on communication. And we're very fortunate that we've gotten a little bit of that time. So that's a long way of saying, and I got to cut myself off here, that we're not going to be able to cover everything in this conversation. But I do want to build off of that answer because, or that piece, because I think there's a couple of things in here that we'd like to explore. I think the short question is, can we make man-made infrastructure to address those climatic changes here in California, like on the scale that we expect to see them? And I do think that it's also a little confusing for people, because I think what we've seen in the recent record, if you're looking over periods of a decade, that our amount of precipitation isn't changing dramatically. What is changing is the timing and form of that precipitation. So I guess it's a sort of two-part question. Do we expect to see that trend continue and become even more extreme, right? Again, not necessarily a big change along the lines of what you just described. Instead of an average of 20 inches a year, sort of, it's coming more boom and bust, right? But then I do want to get into, you know, what are the prospects of the ability to sort of infrastructure your way out of it with gray infrastructure versus do we need to think more about how do we quote unquote roll with the punches and be more prepared to respond to the extreme that Mother Nature is going to present on the dry side, on the wet side. So I'll cut myself off with that question there. Again, I think really maybe more focus on that infrastructure question.
Yeah, and I'll mention I do have the ability to go a little beyond the hour if that lets us answer an extra question or two, depending on the webinar logistical constraints. You know, and so the short answer to the first part of your question, I think, is yes. We expect to see further increases in what I would call hydroclimate whiplash, another term that somewhat colloquial term that we did quantitatively define in our recent review. But essentially this notion that one of the signatures of hydroclimate change in a warming climate, not just in California, but globally, will likely be increasingly frequent and wide shifts from anomalously dry to anomalously wet. And this will occur even in places where there is not necessarily a large or even well understood shift in average precipitation. And this is the case in California, where there is actually still sign change uncertainty, meaning that we don't know whether average annual precipitation might actually increase a little bit or decrease a little bit. It actually could be either. But a lot of folks, I think, and I've seen this, I saw this in California water for a number of years. I think it shifted recently, which is good. But that was interpreted as meaning we don't really have any information to go on regarding changes in hydroclimate. And so we should kind of just assume that we'll see plus minus 10% precipitation, and that's good enough to stress test our systems, and that's good enough to sort of plan for the future. And of course, as you probably can already guess, I just don't think that is true and has never been true, because those very same projections that yield uncertain changes in average precipitation, you know, plus minus 10, 20%, relatively small, and also uncertain in sign, suggest very large increases in the wettest events and also significant increases in the driest events. Again, these are not different projections or different models. It's the very same modeling tools that tell us both things, essentially saying, well, your water cycle is accelerating, but the mean or the median is centered roughly in the same point, which is actually pretty interesting if you think about what that means, because it means that the water will still come. We probably won't have a future where it just completely stops raining in California. And I know that had been a lot of people's fear. It does not appear to be a particularly likely outcome. But that said, I think that then, on the other hand, some folks have really underestimated the profound nature of the changes that we are likely to see and are already beginning to see by some metrics, but this increase in whiplash and variability and volatility and these swings. And so I think that in particular is likely what we really need to be thinking about preparing for. rather than just a sort of a contiguous drying or wetting trend, respectively. We really need to be thinking about both increased variability and how do we manage that, and what infrastructure is or isn't commensurate with that kind of challenge. And so the answer to the infrastructure question, I think, is probably a mix of both. And a lot of folks say, okay, with more variability, don't we need more big dams? I think the problem with that is there's two different scale mismatches, I think, that come into play. One is the realization that even with California's very large dams and reservoir system that already exists, most of California's major rivers have dams on them somewhere already. Most of the sites that are effective for capturing large volumes of water relatively safely on large rivers in California already are used to do so.
Mhm.
Even those capture a pretty small fraction of the runoff that occurs in a wet year in California. So most of that water is not storable because it already comes in such big pulses that you can't necessarily store it behind, you can't double the height or triple the height of Shasta Dam, for example. It just is not a practical, reasonable, safe sort of engineering
It wouldn't
prospect.
meet the scale of the challenge, even if you did that. Is that?
It's So you couldn't really meet the scale of the challenge that way. But also, you know, in a more volatile hydroclimate on the wet side of things, so we're often thinking about water scarcity risk mitigation, right? Like drought mitigation. Like how can we store more water for the lean times, for the dry times? That's reasonable and is a major piece of this. But the other side is how do you manage flood risk during the increasingly big bursts? And one challenge is that trying to build ever more substantial dams and flood control systems becomes uh, complicated as well from a safety perspective. If you have these huge and increasingly large pulses of water, especially if you have dams that were designed for a climate that produced less frequent or less large extreme pulses of water, you then have to think differently about kind of your safety margins and how you design the dam infrastructure and the outflow structure and the downstream levees and all of that. So I think that there is a limit to how much new large reservoirs can provide us because they're primarily good at storing snowmelt, gradual snowmelt, and continually replenished in the spring and summer months on the west slopes of the Sierra, for example. But we're going to see less reliable, more rapid, earlier season snowmelt. So those reservoirs become less good at their job of helping us store water for the dry times. Likewise, the increasingly large storm pulses make it a little bit riskier to rely on such big dams. So there is that consideration. There probably are some places where off-stream storage maybe is a little bit of a different challenge and maybe a little bit less risky, a little bit more interesting of a prospect. But even here, there's the scale, the volume question, and the cost benefit analysis of, okay, well, if we build a new off-stream reservoir to store water for the dry times, how much would it have cost to find that water somewhere else, either through increased efficiency or, reuse of that water, or in some cases, things like groundwater banking, which can even be used in some cases in a way that is commensurate with our increasingly whiplashy future, which is to say, in conjunction with floodplain restoration and river channel restoration, whereby you can do something called flood-MAR, so flood managed aquifer recharge, where you call them excess flow or flood flow when it's really wet, redirect it somewhere of your choosing, so not just randomly, but to a particular location where it will either do the least harm or provide the most benefits, or both, ideally, where you might help protect places you don't want to flood from flooding during those events, and also find a way to store some of that water underground in aquifers so that it recharges those aquifers so that you actually have more water stored during the dry times that follow. And so you can kind of see how that's particularly aligned with a climate that sees more of both wet and dry extremes. You're kind of managing the risks of both all at once. But on the other hand, in urban areas, right, in places where you really don't want to flood, you really don't want to flood Sacramento or any number of other Central Valley cities. And so you do want robust flood protection. And so my thinking is sort of essentially this, which is that new big dams probably won't help solve our problems in a safe or cost-effective way in the same way that they did, at least initially, with the first ones that we built, especially in a warming climate. But that, on the other hand, we probably do need increasingly robust flood protection infrastructure. We probably do want to ensure that our levees and our dam infrastructure is up to the challenge of a 21st century climate. And that does involve likely new building and new engineering projects to ensure that that happens. But there are these other places where, it's natural infrastructure, floodplain restoration. We have a great example with the Yolo bypass, of course, in the Sacramento Valley, which is not a climate change intervention per se. This is an old construction, but it's been really effective at protecting Sacramento over decades and providing environmental co-benefits where there's this, that's why you drive on the causeway between Davis and Sacramento, is because there's this area that is designated as a place that we want to put water here instead of in the city of Sacramento. And historically that's worked well. Can we do more like that? Can we expand that to include not just floodplain expansion, but also groundwater, banking, doing two things at once, and also having some environmental co-benefits. So I think it's a mix of the above. And I think, when it comes to the life safety aspects, we probably do need new engineering projects. When it comes to managing flood versus drought risk, that may be more a question of sort of expanding, and as you say, rolling with the punches, letting the water do its thing in a semi-controlled way.
Thank you. I think for those of you who are not familiar from outside the region, a lot of what Dr. Swain was talking about there is Folsom Reservoir has a capacity of about 1 million acre-feet, but in the winter, when the rain's coming, we only use 50% or so of that capacity from a supply standpoint, because the remainder really is focused on a flood control operation. And that worked well historically. The way that I describe this is because that big storm event was leaving a bunch of snow on the mountain. That big storm event in the future, and correct me if I'm wrong, Dr. Swain, on this, isn't going to do that with the same level of reliability. That's not to say we'll never have snow again, but it's that the typical pattern of those big storm events being snow driven in the higher elevations is not what we can expect moving forward. So we run into this challenge where a facility like Folsom was historically able to do sort of these two diametrically opposed things of operate for supply and flood. And now it's going to be asked to do both of those things at the same time. And that's not really possible. So we have to come up with other paths here. And so I do want to say here, right, from RWA's perspective, what we've been working on is taking a whole of watershed approach where we're mindful of that, but really like our path forward from our thinking is do more conjunctive use, do more surface water reliance at wet times, and then that allows you, and less groundwater reliance in those wet times, and that allows you to shift over to groundwater in those dry times. I think that's a question of, and correct me if I'm wrong, scaling up. And there are policy challenges, though, on that question on how you scale up. I would highlight one, and sorry if I'm taking over here, but we will get to another question in just a second. I would highlight one that was in a Cal Matters article yesterday, which is, I'll describe the challenge the same way more or less as was highlighted in the Cal Matters. If you put water in the ground, there is no ownership of it. You're benefiting everybody in that region that has access to that groundwater. If you put water in a reservoir, there's clearly identified ownership of it. That is not a water problem so much as a human, how do we manage that water problem, I would argue. And I think that there is an ability to break down those challenges that the human side has created so that we are creating the incentives to adapt to these extremes. I will work in a question here, which is, and I want to come back to the size of the extremes because these are some of the questions that I got in the chat. And my apologies, everybody, I'm not going to be able to sort of ask exactly the questions in the chat. I'm hoping we're getting an amalgamation of those questions. So one of the questions, though, is we've seen extreme events, particularly in Greece, like 12 inches of rain in an hour was what was in the chat. I'm going to take that for its accuracy. I know there was extreme events in Spain. We've seen extreme events in terms of rainfall in the Middle East, like Afghanistan, if I'm not mistaken, and places in that region of the world, the sort of Asian Southeast. And you mentioned at the top, right, that there's this exponential ability of the atmosphere to hold on to water. And I'm assuming that those events are really sort of an expression of that climate change. And you mentioned, right, 1 degree, 3-4% expansion. How much more water is the atmosphere holding today? How much more water do we expect the atmosphere to hold, assuming no change in emissions, 20 years down the line, 50 years down the line? I guess that's a not eloquent way of asking a scientific question of how extreme can we expect the events to be in relative to the historical past. And I do want to work in a question here because we really manage based on historical models. How invalid are those historical models is more or less the question that I'm asking. But the other part of the question is how much more extreme, like what is the thing that we're missing here, or that from your perspective that we don't think about, even as professionals working in this field, to be prepared for? Like what is that really extreme event? Like the Arctic storm, the 15-year drought with no rainfall. Like what is that most extreme event that is likely to occur, and likely to occur with the predictive power of the models that we have?
All right, so there's a lot in there, and I'm gonna, in this response, try and also, I just was looking at the Q&A briefly, try and respond indirectly to at least a couple of those additional ones. I'm pretty sure this will bring us to the end of the hour, but again, I can go a little beyond if the organizers can.
We can go a few minutes over.
Okay. So just to respond briefly to what you initially started with the last segment there, it is true that we're going to see, and we already are seeing, substantial increases in the balance of rain rather than snow at higher elevations, which does change the hydrology of storms and inflow into reservoirs. In fact, there's some evidence, if you recall the Oroville Dam crisis back in 2017, that even if you ignore any changes in the amount of precipitation, but only look at the changes resulting from the observed warming trend and therefore the shift from rain to snow in the watersheds above Oroville Dam, that the inflow into the reservoir during that crisis period was probably between about 10 and 20% higher than it would have been had those storms been at a more typical historical temperature. So the warming itself increased the inflow into that dam by about 10 or 20% during the crisis period. I have it on pretty good authority from folks who worked during that event that had the inflow been 20% less, that we might not have experienced crisis level conditions in the first place, because we wouldn't have overtopped the emergency spillway. The flow down the dirt slope probably wouldn't have been as erosive. But also, I posed the corollary. Okay, so what if we were 20 or 30 years in the future and the same thing had unfolded and there'd been an additional 10 to 20% increase in the inflow during that event? So a total 20 to 40% increase in inflow. Would that have gone from a crisis fortunately averted to an actual catastrophe? And nobody knows the answer for sure, of course, but that certainly raised some eyebrows. So a way to think about that is, yes, this can have consequential effects, especially when things don't go well. Even in less dramatic circumstances, it definitely affects when we're getting the snowmelt, how large those snowmelt pulses are, how effective our Sierra West and, I guess, Northern Mountain south-facing slope reservoirs are on collecting that water and giving to us when we need it. There is one additional intervention that is potentially promising and has been advancing, which is forecast-informed reservoir operations. Essentially, in places where this has been implemented, this is a way of threading the needle and not needing to keep such a large flood pool, essentially the flood safety pool, in place at all times, because historically it was assumed that a big flood could happen at any moment with almost no warning. And so you needed to maintain a flood pool big enough to accommodate that very large flood, even if you were 99.9% sure that it wasn't going to happen in the near future. Forecast-informed operations allows you to relax that constraint a little bit and say, okay, due to the specific weather forecast right now, and weather forecasts have gotten really good in recent years, there's not going to be a catastrophic flood event in the next few days. So we don't need to behave as if there will be. Now, if there is a real potential for a big flood, then of course, then they say, okay, you really do need to make sure you have that flood space and release that water in advance. That's another potentially essentially reoperating existing infrastructure using increasingly sophisticated weather forecasts is actually a very good use of effort and money and resources, because it does not necessarily require big new construction projects, but it is probably one of the more useful technological solutions in that space. Now to jump to the sort of the other side of this, I just talked about the thermal and the rain versus snow perspective. What are we thinking about in moving forward? One of the interesting things is that historically so far, we have seen a larger increase in dry extremes in California than wet extremes. So wet extremes, there's data, essentially, I'll call it. There are certainly record-breaking rain and extremes we've seen in recent years, but the long-term trend, I guess you could say, isn't statistically significant. So it doesn't pass, 95th percentile, 99th percentile confidence. But we have seen enough unprecedented rain events recently. I think we're starting to see the early stages of that side of the hydroclimate coin accelerating too. And what do we expect in general? Well, 7% per degree centigrade, or about 4% per degree Fahrenheit, is a good heuristic. It's a good baseline estimate for how much the intensity of the most intense rain events should increase on average in aggregate in a warming climate, not for how much rain we get overall. That may not even change at all, but for the most intense downpours, about 4% more intense per degree Fahrenheit. And of course, we're already a few degrees Fahrenheit warmer than we were historically. So what's interesting is, for the very most intense events, some of our own research suggests that if you look at, a 2 or 3 day atmospheric river storm, those do intensify by pretty close to that rate that you'd expect, 7% per degree centigrade, 4% per degree Fahrenheit, something like that. But for the very most intense hours of the most intense storms, so that the worst part of the worst storms, essentially, they intensify at about double that rate. So more like 14% per degree centigrade, or about 8% per degree Fahrenheit. That, I think, tells us something about the character of the flood risk we'll see in the future. That starts to shift the risk from slower responding mainstem river flooding to more flash flooding and debris flows, especially in urban areas and in steep, flashy, fast responding watersheds. So that's maybe an underestimated risk. And actually, we have seen more of that in recent years. Those are the kinds of events that we've started to see record-breaking 1 hour, 12-hour, 24-hour precipitation totals recent years, even though we haven't seen the record-breaking, multi-day totals yet. And finally, I would mention that in terms of, what is the plausible worst case, we have designed in a contingency planning scenario, which is essentially an extreme multi-week storm scenario, one for the historical climate of California and one for the warmer future climate, characterized by warmer storms and more intense storms, called ArcStorm 2.0. And there's a number of resources on the web. We have a peer-reviewed paper that came out in 2020. I have a number of blog posts. There's a bunch of news articles about it if you want to learn more. This is a project that has continued to evolve. In fact, there still is involvement with the California Department of Water Resources and other state agencies in this ongoing work to assess sort of a reasonable plausible worst case for what an extremely severe statewide flood scenario would actually look like. And we have done some initial work on this. There is ongoing work, but I think we don't have a full picture yet, because of course the last time we had a flood of this magnitude was actually in the 1860s. And we of course didn't have 40 million people living in California then. We also didn't have modern flood control infrastructure. So the extent to which those risk factors offset each other remains to be seen. But I would finally add that just because we've seen big floods in the past, just because the Great Flood of 1862 happened, before human-caused climate change, does not mean that we should not be worried about increases in large catastrophic floods in a warming world, because, as I mentioned, there have been crocodiles in the Arctic and palm trees in the Arctic before. Doesn't mean that it would be great if we suddenly entered a period where there were now suddenly enough warmth to see that again in the Arctic. It's that change based on what we're used to, the non-stationarity of things, that is the big challenge. And so I do think that we've focused a lot on drought and wildfire risks so far, which makes sense. We've seen a lot of them in recent years, but we ignore the increasing risk of severe floods in California at our own peril. And just because that big increase hasn't yet clearly manifested itself does not mean that it's not coming. In fact, there's even some scientific evidence that it's been a little bit artificially suppressed by some natural climate variations in recent decades that will sooner rather than later most likely disappear, and we will unearth that sort of erstwhile increase in flood risk that's occurred in the meantime.
So I know we're a little bit over, and I want to give you just like a couple of minutes, and I'm hoping to end on a slightly positive note. So I'm going to ask a positive question, and this will be the last one. And my apologies that we didn't get to everything. I think we knew that we weren't going to be able to do that. But hopefully I feel like I got a lot of good information. So I do want to say thank you. I do want to acknowledge for everybody that once Dr. Swain answers this question, we're just black screen after that. So it ends somewhat abruptly. But the question that I want to ask is, what does success look like in terms of climate response? What makes you optimistic about our ability to be successful 10, 20, 30 years down the line? What do we do over the next quarter century? What is the reason for you? Why can you maintain optimism in such a sort of scary, maybe even negative space? So
yeah, I think that's a good note to close on. And in so doing, I'll also add that for folks who didn't get their questions answered, that I do host sessions similar to this. I call them my live virtual weather and climate office hours on my YouTube channel with some regularity. I don't have a session this week because there's lots of other engagements this week, but that'll begin again next week. And you can ask certainly some of these questions in that setting later on as well, and I'm happy to answer them. Similar Q&A format there in the chat. I think the whole purpose of trying to predict the future, whether it's in terms of climate change or anything else really, is to sort of improve that future relative to what might otherwise take place. And it's not necessarily to say that I'm brimming with unbridled optimism about the way things are currently evolving, but it is also to say that you always sort of have to work with what you've got, start from where you are and try and make things better from there. And an important part of that is being honest about how things have changed, our best estimates of how things are going to change, because we need to understand that to make good and, dare I say it, efficient choices about the future. I know there's a lot of talk these days, in the US about efficiency, but what does that really mean? Part of efficiency, cost efficiency, resource efficiency, time efficiency, mental anguish efficiency, whatever the metric is ideally correctly anticipating future needs, preparing for them in advance, and then either preventing bad things from happening or making them at least less bad than they otherwise would have been, as well as facilitating even good things, dare I say it, depending on the situation. And I think the reality is that a lot of this is achievable, especially in a case like California's, where there are a lot of resources, there's a lot of smart people working on complicated problems, and a lot of willingness to try new things. That's one of the things that California has been famous for over the years, is experimentation in the public policy sphere, in the environmental sphere, and elsewhere, which is exactly what we would need. And so I think the reality is this is something that can be done, but in order to do it, we have to be honest about the changes we're going to see. And part of that is embracing variability. It's acknowledging whiplash and acknowledging complexity. And I've said the same thing about wildfire risk, about flood risk, drought risk, all of which are things we face in a warming climate in this part of the world, especially. To successfully mitigate the societal and effects or harms of these things as they become more frequent or more intense, both as a result of a warming climate and frankly for other reasons as well. It's the same logic applies. We need to acknowledge what the underlying drivers of those trends are. And if those drivers are multifactorial, if it isn't just one thing, but it's a range of factors, we need to be addressing each of them independently and in a way that addressing one of them doesn't actually increase our vulnerability to the other. And so all of the things we've talked about today, specifically are interventions that are commensurate with that increased variability, that are specifically in line with the non-mean state changes, the whiplash, the expanding atmospheric sponge, the variability that we are beginning to see now and will continue to see in the future. So I think that there are ways to address all of these things. It might involve behaving differently and thinking differently than we have historically, but that's doable. That can be done. We just really need to pick up the pace a bit, I think, is my message today.
Again, thank you. And thank you all for attending. Really appreciate it. Please see in the chat, I know it's only for a second, the ways in which you can access some of Dr. Swain's ongoing work and his leadership as a climate communicator. So please, everybody, stay engaged on that front. And thanks again, all. Appreciate it. We'll see you later.